Welcome to chapter 17. We're going to be talking about carbonyl chemistry. So the chemistry, this is the carbonyl, and it is a part of a ketone and an aldehyde. An aldehyde has the hydrogen there. And that is what we're going to be talking about, the chemistry of carbonyls. So right here, this is oxidation. So this is an oxidation reaction, and this is a primary benzylic alcohol. And the functional group transformation goes to an aldehyde. Now remember, aldehydes on the oxidation pathway are hard to do. So you need a mild oxidizing agent. So PCC is that mild oxidizing agent. Lithium aluminum hydride, that's a reducing agent, so it's going to add hydrogen hydrides to the carbon. Sodium borohydride is also a reducing reagent. The other oxidizing reagent is potassium permanganate, and you see that the manganese has oxygen. All right, this is electrophilic addition. Functional group transformation is an alkyne. The alkyne is going to a ketone. So if you remember, this goes through an enol. So there's the enol, and then it goes through enol tautomerization. This is an enol, so this goes to there. And if you remember, that tautomerizes to the ketone. Which reagent does that? Mercury sulfate and sulfuric acid. This is a terminal alkyne, so you should remember that the diisoamyl boron and sodium hydroxide and hydrogen peroxide would make an aldehyde, and this is organic 1 material. Okay, another ketone. A ketone from a benzene ring. So these are the functional group transformation. This is Friedel's Craft. Acylation. So to make a strong electrophile, you need an acid chloride and a Lewis acid, aluminum trichloride. That makes the aselenium ion. That's your electrophile. And if you remember correctly, this goes through a sigma complex mechanism there. And you have the hydrogen here, positive cation, and then the aluminum 4 chloride will then do the re-atomization to give you your ketone. And so this is your acid chloride and Lewis acid, C. All right, so that's just an example of functional group transformations from other functional groups to make ketones and aldehydes. And this is chapter 17. So not only do we need to know how to synthesize these functional groups, we need to know the reactions where these are starting materials and they go to other functional groups. So this is just showing you an aldehyde and a ketone. The R just means any carbon containing chains. Carboxylic acids are also bonded to the carbonyl, and we will talk about chapters. We'll talk about the carboxylic acid, and we'll talk about their derivatives. Acid chloride is a carboxylic acid derivative. and an ester and an amide. And these will behave very similarly, and we'll talk about those reactions. But this chapter is really going to focus on aldehydes and ketones. They're showing you here that this is electron deficient. So if you were to draw a a resonance structure where the pi electrons go to the oxygen here, you would see that that gives a full positive on that carbonyl carbon. So the carbonyl carbon is an electrophile. And so that's your electrophile. So you will be reacting different nucleophiles to this carbonyl carbon electrophile. And this is an sp2 carbon, and the oxygen is an sp2. So these pi electrons, the pi bond is in an unhybridized p orbital. And this is just showing you the resonance structure that I just showed you, where you have an electrophilic carbon. Now, the pi bond here, this electrophilic carbon, this is pretty much uncrowded. And you'll see that aldehydes always have a hydrogen here. And this is going to be less crowded sterically than a ketone, because the ketone has these methyls. So keep in mind this is rotating around a single bond. And so if you even get more carbon here, and you get this chain and they're rotating, and every one of these are rotating, you can get very crowded conditions, sterically hindered conditions around this electrophilic carbon. But aldehydes always have a hydrogen there on one side. So hydrogens are going to be less, aldehydes will be less sterically hindered than ketones. Now, because we're going to be doing nucleophiles, and nucleophiles, different nucleophiles, add to the carbonyl carbon, and they're less sterically hindered, the rate of reaction is going to be such that typically an aldehyde is going to be about 10,000 times faster reaction than a ketone. So they're going to be more reactive. And this is because of the steric hindered. And this is showing you we're undergoing nucleophilic addition. So this is step one. So we'll add different nucleophiles. And then what happens is, this is going to be your mechanism. You're going to have, let's say you have this aldehyde. You need to have your lone pairs. And then let's say like you have sodium borohydride. So if you draw sodium borohydride's Lewis structure, it would look like this, where this is negative, the sodium is positive. We don't draw lines there because it's not a covalent bond. So this basically delivers a hydride as the nucleophile. And so you can just do that. This is going to nucleophilically add. We'll go straight up here. And so the electrons go on the oxygen, and then we've added this hydrogen. This is a tetrahedral intermediate, and you're going to have these. You're always going to have the tetrahedral intermediate for nucleophilic addition. And then you need to add a proton source, usually water, and then it protonates to make, in this case, a primary alcohol. This mechanism is called nucleophilic addition. And you can say not just nucleophilic, it's acyl nucleophilic addition. Now, we're not going to talk about this until the next chapter, But when you have a carboxylic acid and their derivatives, you the this the it ends up being a leaving group. So this becomes nucleophilic substitution. So, and this will be a different mechanism. So this will be acyl nucleophilic substitution. So we're going to focus on aldehydes and ketones in this chapter, and they're undergoing nucleophilic addition. So the nucleophile is going to add to the carbonyl carbon. Um, we just did an example. Okay, so the nucleophile is going to add to the carbonyl. It's delta positive. And those electrons, you see the curved arrows, you need to show the curved arrows. This is your tetrahedral intermediate. And then the second step, you get protonation, and this is nucleophilic addition. So this is acyl nucleophilic addition. Aldehydes are less crowded, less stable, more reactive. I said it's about 10,000 times more reactive than like a ketone, because these are electron donating groups and they're rotating, and it makes it hard for a nucleophile to get into the electrophilic carbon. It's got to get in there, and it's actually the Burgi-Dunget angle. So this has been studied. I think it's 107-degree angle in which the nucleophilic acid attack, and because ketones are more crowded, they're going to be more stable, which is good for ketones, but they're going to be less reactive. All right, we'll just go forward. So here's the example of this mechanism, and this is acyl nucleophilic substitution, and this is when we have a leaving group. You get this with the carboxylic acid derivatives. So we won't be really looking at those. You see these are carboxylic acid derivatives where the Z is an OH or acid chloride or an ester or an NH2, and then it forms the same tetrahedral intermediate, but the carbonyl reforms, and whatever is on the carbonyl is a leaving group. Now, aldehydes and ketones don't undergo that because H is not a leaving group. Okay, so that is not going to be a leaving group. So basically the nucleophile will add, and that's where the addition comes in, and so it stays. So when you have a nucleophile add and it gets protonated, so whatever nucleophile you add, you notice the H stays because it doesn't leave. Same thing with ketones. Ketones, you have a nucleophile that adds, but notice this CH3 is going to stay. So that'll get protonated, the nucleophile is going to add, but the CH3 is not a leaving group, so it stays. So this is nucleophilic, acyl nucleophilic addition. Carboxylic acid derivatives, which we'll talk about next, undergo substitution, acyl nucleophilic substitution, because when the nucleophile adds, you have a leaving group here, and so you reform the carbonyl. And then you have the nucleophile substituted, and you reform the carbonyl. Nucleophilic acyl substitution. And so this is showing you the leaving group ability. Acid chlorides are going to be the most reactive of your carboxylic acid derivatives because chloride is your better leaving group. And you'll work some Pogels on that. Esters are next, and then carboxylic acid. You're going to have to probably add some acid in order to protonate that OH to make it a good leaving group. And this is called an amide. And amides are least reactive because the leaving group ability of an NH2 is very weak. So they're just showing you the two different types of mechanisms. Aldehydes undergo nucleophilic substitution, do not undergo substitution. It's because this is not, the H is not a leaving group. So when the nucleophile adds, so when you have your nucleophile add here, this can't happen, you see? This is not a leaving group. All right, so nucleophilic addition of carbonyls, the intermediate is always a tetrahedral intermediate. So let's look at this. Where's your nucleophile? Do you see that this is actually called a Grignard reagent after Dr. Grignard, and it makes a negative carbon here. So this is your nucleophile, and this is your electrophile. And so the nucleophile adds to the electrophilic carbon and forms a tetrahedral intermediate. So you need to draw your curved arrows. You need to draw your tetrahedral intermediate. Tetrahedral means there's four things. So I need to see the four things. You can write tetrahedral intermediate. And then, because hydrogen, there's no leaving group on this, you quench it with a little acidic water. You do this in your reaction flask, separatory funnel, and the OH is formed. So there's your hydrogen, and you still have an H, and you have a CH3. So you'll see that this is a secondary benzylic alcohol. That's your functional group transformation, and that is answer B. All right, so we just did this reaction here. Let's work this one here with sodium borohydride. What you need to do is you need to see that this is a nucleophilic hydride. This is your delta positive. So the hydride nucleophile will add to your electrophile, and those electrons go up on the oxygen. This forms the tetrahedral intermediate. We need four things on that carbon, and there are the four things. And then you would quench this with, you put a number 2. You're going to have to need a little acid water, just a little bit, so it'll protonate. You can just assume that. If it's not, you never want to leave the charged intermediate. So this is that reaction there. So it is a primary benzylic alcohol. We're going to be doing, this is a strong nucleophile. Do you see this is a strong nucleophile? How do you know it's strong? It has a negative charge on the nucleophile. This is a strong nucleophile. CH3 with the magnesium, whenever you see a metal, you can assume that's positive, which makes the carbon negative. This is a weak nucleophile. This is, you know that because there's no negative charge. You have 2 lone pairs. This is organic 1. If you need to review weak and strong nucleophiles. So that's a weak nucleophile. And what you're going to have in that case is you're going to have some acid catalyst. And so in that case, you're going to add an acid catalyst for this reaction to occur because you have a weak nucleophile. And in weak nucleophiles, you protonate the oxygen. So this oxygen is going to get protonated. And when the oxygen gets protonated, the oxygen becomes positive. And this makes it a stronger electrophile. So, and you can see that by the resonance structure here, where those electrons go there. And you now have a full positive charge on the electrophilic carbon. Well, now this nucleophile can come and add. There's the OH, there's your H, O, CH3. In this case, then the water that became H3O plus here can deprotonate and this is a new functional group. You see that carbon is bonded to an OH and an OCH3. That's 2 oxygens. This is a new functional group. It's called a hemiacetal. Okay, so preview of oxidation and reduction. So how do we make, how do we synthesize aldehydes and ketones? Typically, one of our best ways is to oxidize an alcohol. So if we have an alcohol and we add an oxidizing reagent, then we can make an aldehyde. This is review. PCC does that. Or we can go all the way to the Jones reagent, which is the chromium, and we can make a carboxylic acid. Now, we can also go the opposite way and make an alcohol. So if our starting material is an aldehyde or a ketone, we can do a reduction reaction. And so that's sodium borohydride, or a really strong one is lithium aluminum hydride. And these are hydride delivery reagents. They deliver an H minus. Okay, so starting with methanol, stepwise oxidation to carbon dioxide. So this is a methyl alcohol. And so you see that carbon has 1 bond to oxygen and 3 bonds to hydrogen. When we oxidize this, you can oxidize it with PCC or Jones. Well, let's just do PCC. If you take away the hydrogen and you make another, so you minus a hydrogen and you increase the carbon-oxygen bonds. And so this becomes, so here we have 3 carbon-hydrogen bonds. Here we have 2 carbon-hydrogen bonds. Remember, carbon gets 4 bonds. So we have 1 bond, 1 carbon-oxygen bond. This has 2 carbon-oxygen bonds. This is an aldehyde. And then we can take away another hydrogen and do another oxidative step where we increase the carbon-oxygen bond. And that functional group would be a carboxylic acid. And that is what Jones could do. So that would be a Jones reagent, which is the chromium and acid. And we still have 1 carbon-hydrogen bond. We have 3 carbon-oxygen bonds. So now we can still oxidize this more, and that would be carbon dioxide, and that's how we get 4 carbon-oxygen bonds. This is a fully oxidized carbon. What is the major organic product? Okay, so now this is going to be acyl nucleophilic substitution. So we're just going to show that here, substitution, where this is a positive, this is a negative. because you have a leaving group. This is an ester. So what happens here is the nucleophile will add to the electrophilic carbon you get something like this, your tetrahedral intermediate. Now, since this is a leaving group, we'll reform our carbonyl when that leaves. So leaving group, and we reform the carbonyl. When you have, this is going to be substitution. And so now we've substituted the OCH3, we've substituted this with a CH3. Now, this is a ketone, and you know ketones, you still have this Grignard in solution. And this Grignard is going to be more reactive towards a ketone. So the ketone is more reactive than the ester. See? So here's your ester. This is more reactive. So what's going to happen is now you're going to get nucleophilic acyl addition. You have the CH3 here. Now you've added another CH3, and this is your tetrahedral intermediate. And then you have the acid and water, and that will get protonated to make a tertiary alcohol. So C is your answer. Okay, so that was just a little side note. Oxidation and reduction of carbonyl compounds. So if this is an aldehyde or ketone, you're going to reduce it. If you're an aldehyde, it's going to reduce. Like, so if you use sodium borohydride, which is a mild reducing agent, delivers the hydride. We've done that mechanism. That is going to make a primary alcohol. If you have a ketone and you deliver sodium borohydride, you will get a secondary alcohol. Reduction of carboxylic acids, you have to use really strong reducing agents. Very hard to stop with the aldehyde, and this is talked about in later chapters. Oxidation of alcohols to carboxylic acid, this is the Jones reagent. You have already gone through this one. Okay, so reduction of aldehydes and ketones, we're going to deliver the hydride. So these are reagents to deliver a hydride. This one's going to be mild. So if you can use mild, you want to, because you can use solvents like methanol. Lithium aluminum hydride is a very strong, harsh reducing reagent, and it also delivers a hydride. You have to use special solvents like THF, tetrahydrofuran. This one's also like a sodium hydride, would also be an example of a hydride reducing agent. But you have to be concerned, like if you get this in oxygen or water, it will catch fire. Most people like the sodium borohydride. You might actually do some reactions in your class using sodium borohydride because it's not so pyrogenic, fire causing. All right, so sodium borohydride, lithium hydride, and then you always quench these with the water because the tetrahedral intermediate makes the O minus. So you're always going to have to quench that with water. So usually you 1 and then 2. And you'll get a primary or secondary alcohol. This is just showing you the mechanism here, and we have gone over it, but you can look at it again. Catalytic hydrogenation, I don't teach this with aldehydes and ketones. It's very hard to do, and you want to basically do this reaction and these reagents with alkenes and alkynes, and they're really great for making alkanes. And that's what they're saying is the carbonyl is reduced with sodium borohydride and lithium aluminum hydride, but the carbon-carbon double bond is inert. So this is an example. If you use sodium borohydride, then you're going to add the hydride to the carbonyl to get an allylic alcohol. And we just don't even worry about this one. If you add hydrogen and palladium and carbon, it's very hard to control the equivalence of hydrogen gas. It's going to reduce the ketone, and we'll add those hydrogens from the alkene to an alkane. And notice it does not do anything, this reaction does nothing to the carbonyl. Okay, so sodium borohydride, this is an example of this muscone. It's unowned because of ketone. And we have a ketone with sodium borohydride. You get to do that in methanol, and you make an alcohol. You see the secondary alcohol. And this makes ibuprofen. Here, sodium borohydride, you notice we have a double bond here, but it doesn't touch the double bond. And so it delivers the hydride to the carbonyl, and you still get an allylic alcohol. Stereochemistry of carbonyl reductions. Well, this is sp2, and your nucleophile will come in at the top, and it will also come in at the bottom. And so you get an sp3 carbon. It's a new stereogenic center, but it's going to be racemic. You're going to get equal amounts of the S and the R. Here the hydride comes, they're just showing you from the top or the bottom. When you draw your product, you don't have to draw with the dashes and wedges. I assume that if it's written like this, like we could see that that's a stereogenic center, and when you draw it with just the straight line, you're saying that it's racemic. If you do draw one of these with the dashes and the wedges, I expect you to draw the other enantiomer as well. So you can either draw the straight line, and we'll assume it's racemic, or if you draw one, you got to draw the other. And this is just the way it is for communication in organic chemistry. The straight line assumes it's racemic. The dashes and wedges say you're going to get an enantiomer. So if you're going to draw the S enantiomer, well, you're going to have to draw the R enantiomer too. If you want an enantioselective carbonyl reductions, there are some chiral reducing reagents that can do that. Here's an example. This is a hydride delivering reagent that delivers it from one side only. And you can actually specifically order the S or the R. And these are our auxiliary reagents that will allow an enantioselective, so one enantiomer is selected, either S enantiomer or an enantioselective R. These are also called asymmetric reductions because it only delivers from one side, not symmetric. The CBS stands for C for Cori, B for Bakshi, and S for Shibata. So in just a little tree of organic, I am actually a Cori granddaughter. Granddaughter means the lineage of someone that actually, so my master's degree researcher worked under E.J. Corey for 4 years. Now this is a big deal when you're trying to get jobs as a chemist, because if you're 1 degree or 2 degrees away from, this is a Nobel Prize winner in the 1970s, and you learn a way of working in the lab that's um, given handed down by generations. So, but anyway, you'll see that Corey was a physical organic chemist. Actually, the author of your book, who's from Hawaii, she was actually a Corey daughter. So she actually worked under E.J. Corey. E.J. Corey was at Harvard. But anyway, um, they're just showing you that this S reagent will deliver the hydride from only the front, so you get one enantiomer or the other. So we're not going to worry about this, but just so you know, a percent EE is an enantiomeric excess, and when you use asymmetric reagents, you need to report not only the yield, but 97% EE means you get the R enantiomer, and 97% in excess over the S. Um, this is showing you that reagent where the carbonyl is reduced for one enantiomer over the other. Biological reductions, NADH is a hydride deliverer. So if you've seen NADH in the cells, it's a coenzyme. And if you look at this, you'll see that this is adenine. So think of it like your ATP with the ribose sugar. This is adenine nucleotide with a diphosphate and another sugar, but this is the nicotinamide, and it's this hydrogen that is delivering. So when this hydride leaves, look at this, when this hydride leaves, you get re-aromatization. So this becomes aromatic. And so that's showing you that. So this delivers the hydride, and when that does that, these lone pairs then go into the ring to make pi electrons to push that out. And now you have an aromatic pyridine. Well, it's pyridinium. So this is how our biological systems deliver a hydride to a carbonyl. Where do you see NADH? In the reduction of pyruvic acid. Keep in mind you have an carboxylic acid. This is not going to undergo reduction, but the hydride is going to attack the ketone. And so you see how you deliver the hydride. Now, our biological systems do everything pretty much asymmetric. So you're going to get only the S lactic acid formed. And this is just showing you vitamin B3 is synthesized, well, NAD plus is synthesized from the vitamin B3. Okay, other metal hydride, dibal. Dibal is this diisobutyl. So you see this is isobutyl, and you see there's two of them. So there's the diisobutyl aluminum hydride. Dibal H, it makes a mild reducing agent. So if you use dibal, usually you use at minus 70 degrees, and it will only deliver one hydride. You can also see different derivatives of lithium aluminum hydride, like this turbotoxic aluminum hydride. And this will, because lithium aluminum hydride is so strong of a reducing agent, it will reduce all carboxylic acids. But if you use dibal, you can take a carboxylic acid to an aldehyde. And that's a big deal. I told you anytime you can reduce to an aldehyde or oxidize to an aldehyde, it's great. So a lot of times you'll see this is just written as dival H. What is the missing reagent here? Well, look at the functional group. So we have a ester, and the ester still is intact. So we have an ester there. Even though it's turned upside down, it doesn't matter. We still have the double bond. Okay, so the double bond has not been reduced. And then what's happened is this aldehyde has now gone to an alcohol. So when you go from an aldehyde to an alcohol, you got to decide, is that oxidation or reduction? That is reduction, right? So you need a mild hydride deliverer. So this is good for reduction of double bonds and triple bonds to alkanes, but that didn't happen. This is an oxidizing reagent. It goes from alcohols, primary alcohols, to aldehydes, but we did a reduction here. See, we went from an aldehyde to an alcohol, and so that would be sodium borohydride, because you need a mild reducing agent. Lithium aluminum hydride would have reduced the ester as well. So if you would have reacted this with lithium aluminum hydride, you would have gotten this product. If you would have reduced this with hydrogen and palladium and carbon, you would have gotten this product. Hydrogen added on the same side with the aldehyde and the ketone still intact. Okay, so acid, chlorides, and esters can be reduced to either aldehydes or primary alcohols depending on the reagent. You have a nice Pogel talking about this as well. So acid, chlorides, and esters can be reduced to aldehydes or primary alcohols. So if they go to primary alcohols, it's usually something heavy like a lithium aluminum hydride. If you want to go to the aldehyde, you're going to have to use dival H. Sodium borohydride will not reduce the esters. And so that's what they're talking about here. Lithium aluminum hydride will convert the acid, chlorides, and esters to alcohols. A milder reducing agent like dival, still lithium aluminum, still an aluminum based, converts the acid, chlorides, or carboxylic acids to the aldehydes, and you have to do this at low temperatures. And so this is what these two different reagents are showing you. And you don't have to have all these derivatives. If you know one like dival H, that works for me. Reduction of esters, same thing. You can use a strong reducing agent, lithium aluminum hydride. It's going to go all the way to the primary alcohol. If you have dival H, it's going to stop at the aldehyde. And so this is showing you the delivery of the hydride. You make your tetrahedral intermediate, and then you have a leaving group. So you're going to reform the carbonyl, and then you have a leaving group there, but now you have an aldehyde, and you know aldehydes are also going to undergo nucleophilic acyl addition to give you the alcohol. This is an example of a marine cytotoxin. This is a lot of stereocenters. Probably took someone 4 years every day of their life to make in the lab. And here it just shows you this ester and all this functionality is reduced with dival H to the aldehyde. Lithium aluminum hydride reductions. they're going to go, carboxylic acids will all go to the primary alcohol. So anytime you have a carboxylic acid, lithium aluminum hydride is a strong reducing agent. You have to do lithium aluminum hydride in THF. You cannot use water. But water's put here as number 2 because you have to quench it. And so an amide can also be reduced, but they're going to reduce that to the amine. The hydride will be delivered here to the carbon, and that will get reduced to the amine because that nitrogen is on an OH. And this is the mechanism. You do not have to know this mechanism with the amine at this time. But you do need to get familiar with these reagents and know that lithium aluminum hydride is a strong reagent, and you need to know that it will oxidize, or I'm sorry, it will reduce aldehydes, ketones, carboxylic acids, esters, acid chlorides, all to their primary alcohols. Amides get reduced to the amine. This is an amine, this is an amide. Now, mild reagents are sodium borohydride. Sodium borohydride will only do aldehydes and ketones and will go to their alcohols. Sodium borohydride does not do acid chlorides or esters. You have to use pretty much dival H, and you're going to go to the aldehyde. Keep in mind that what's not here is carboxylic acids and amides. So they're not even included in dival. This is just acid chlorides and esters. All right, so what is the major product? Well, lithium aluminum hydride is not going to it's a reducing agent. It's a strong hydride deliverer. It's not going to touch. It's not going to affect the carbon-carbon double bond. That's more of catalytic hydrogenation. You do have an acid chloride. So it's going to deliver twice. What's going to happen here is this nucleophile will add to the carbonyl. You'll get a tetrahedral intermediate that looks like this. So let's draw our tetrahedral intermediate with the hydride added. And then this is going to, because this is acyl nucleophilic substitution, Cl is a good leaving group. So we were going to reform carbonyl. So when this electrons come down and reform the carbonyl, the chloride leaves, we get an aldehyde. Well, aldehydes are more reactive than everything. So here we take another hydride. It's going to add to the aldehyde, and then this is going to, you got to assume it gets quenched with a little bit of acid and water to deliver the hydrogen. And so that is going to be a primary alcohol. And so B is your answer. Oxidation of aldehydes. Okay, so this is oxidation. Oxidation reagents will deliver oxygen. So this is the chromium. This is your Jones reagent with the chromium. And this is also Jones. And then we got permanganate, which is with manganese. Remember, that was really nice for diols. You get the syn diol. The Jones reagent is really good for alcohols to go to carboxylic acids. And then PCC is really a mild oxidizing agent. And you go to aldehydes. You do not have to do arrows. These are oxidation reduction reactions. This is because of sulfuric acid. This is the Jones. It's got the chromium oxygen with the sulfuric acid. So an aldehyde is going to go all the way to the carboxylic acid. Here you have an example of silver oxide. I don't usually use this reagent. This is showing you another nucleophiles that can add is organometallic. And so anytime you have a lithium, make that a positive, make that a negative carbon. Here is a Grignard. Magnesium is a 2+ in the second group. So it has 2 coordinations. We don't really care about the X here, but it's very important that you know that this generates a strong nucleophile. These are strong nucleophiles. A mild nucleophile is copper. So here's your copper, and it's only going to deliver 1 R group. And these organocuprates are special because they can deliver only 1. So this is going to be a special reagent. And so the organolithium and the organomagnesium are very reactive, so they're very strong nucleophiles. And these are also called Grignard if they're magnesium. The organocuprate is R2, just because that's the way copper is, but you're only going to deliver 1 R group. That's what they're saying here into the reaction. And these all react like a negative carbon, which is a nucleophilic carbon, which is a big deal, and that's a carbon anion. This is how you prepare them. You basically just do like an SN2 reaction. Well, no, I said SN2 because your starting material is an alkyl halide, but this is actually called insertion, and insertion, it just inserts. Lithium will just insert. Magnesium will just insert. But this is, so it inserts between the carbon-halogen bond. The solvents you need to use ethers. Usually you'll see tetrahydrofuran for these metal type. You can't use water. Water will shut them down. No water. No water with these reagents. Organocuprates are a lot like the organolithium. A lot of times you generate this copper salt, but they're going to deliver R on carbon. Okay. Another nucleophile you'll run into is the acetylide. So you remember how to make an acetylide? I called it an alkynide. So this is sodium hydride, which is a strong base, and it will deprotonate this. This is acid-base chemistry because that's a pK of 25. This conjugate acid, pKa, is 35. So you make this acetylide anion, you have a negative carbon now, which is a nucleophilic carbon. So these are nucleophilic carbon. And then this is just showing you organolithium is such a strong base as well. So there's another base that can generate it, but you get your negative carbon. And then, but you can't use water. So they're strong bases. You do not use water. No water. What? You don't even have a drop of water. You get your glassware and all your reactants out of a drying oven, because once you have this, and even this is alcohols. You can't have alcohols either. You cannot have any proton source because you will do an acid-base reaction, and then you will not have a negative carbon. So you will lose your nucleophile. All right, so what is the major product here? Well, you have a ketone. Here's the negative nucleophile. You have a ketone. This undergoes nucleophilic acyl addition. And there's your tetrahedral intermediate. And then this will get protonated with a little bit of acid to generate your tertiary alcohol. Okay, so this is just showing you once again, when you make your Grignard, so an alkyl halide, so let's say you have CH3 bromide and you react it with magnesium, this is going to insert, magnesium is going to insert, so you'll have magnesium and bromide inserted. And this is such a strong nucleophile. If you have a proton, not only is it a strong nucleophile, it's a strong base. So as this is a strong base, anytime you got a proton source, this is going to do an acid-base reaction, and now you have this conjugate acid of the alkane, and the pKa of that is 50. So between 50 and 15, it is like, that's a lot of zeros, like 35 zeros. And I'm not going to draw them all the way to the alkane. So not only are these organometallic reagents strong nucleophiles, they're also strong bases. And so they're showing you here M is a metal. So we've seen the metals, we've seen lithium, we've seen magnesium. We've also seen some copper. And then this delivers the R. So there's your R. And you can, aldehydes and ketones are going to make alcohols. If you have a leaving group for nucleophilic acyl substitution, you have a leaving group like in acid chlorides and esters, it's going to add twice because you're going to get a ketone. Ketones are going to be more reactive than the ester, and you're going to get a tertiary alcohol. So I wouldn't even, the only way you're going to get to stop at like a ketone or an aldehyde is if you use a cuprate. I don't usually teach this, but you can put in dry ice like CO2 and you can convert these Grignards to a carboxylic acid. I do teach this. This is, so if you have something like a Grignard here and you react it, and we've done this before. So now you have this strong nucleophile. This is strong nucleophile, and you have an epoxide. Now keep in mind, if you have an epoxide that's asymmetric, so let's just go ahead and add a carbon here. This is a strong nucleophile, and it's going to add from the least hindered, right? So then in that case, you would get CH3 to that carbon, and then this carbon here would have a CH3, and the OH would be on the blue carbon, and this would get protonated. So that's going to make an alcohol. So these are epoxide openings. Just an example of a Grignard being a great nucleophile, a strong nucleophile. Aldehydes and ketones will give you the alcohol. You always protonate. So you do one and then you do two. The Grignards will do this, and so will your organolithiums. Okay, so let's look at these examples here. What is this? Well, we've talked about this already. This will go here, make your tetrahedral intermediate. And this will get protonated, but there's your CH3. So this is a secondary alcohol from an aldehyde. Okay, this one here is a ester. And so the Grignard is going to add one time, and then this is going to be a leaving group. So you're going to get the addition of that, but it's not going to stay there because you still have the methyl Grignard in solution, and you have a ketone. And ketones will react faster than the ester. So this is going to be a tertiary alcohol. Here, this is a ketone. So here you have nucleophilic acyl addition. And then it's going to get protonated. So that will make, there's your new carbon addition. That makes the tertiary alcohol. Cuprate is going to add one time, once. It's mild. This is an ester leaving group. So when it adds one time, it will stop at the, it only delivers one, it will stop at the ketone. And so this is showing the mechanism that we just went over, where the Grignard adds, makes the tetrahedral intermediate, and then since this is a ketone, there's no leaving group, R and R, then you get a tertiary alcohol. So this is formaldehyde. This is going to be nucleophilic addition because there's no leaving group, and you're going to get the primary alcohol. And then you always have to do this second step where you add the water to quench it. And this is showing you an aldehyde, and it gets a secondary alcohol. A ketone is going to add one time and get the tertiary alcohol. And this is showing you actual real examples here of these different nucleophiles adding to these carbonyls. Here's an example of, this is birth control, ethinyl, because it's a carbon-carbon triple bond, estradiol, which is an estrogen derivative, and here is the nucleophilic carbon adding to the ketone there to make a tertiary alcohol, and you've added the nucleophile. This is another example where a Grignard is added to a ketone. So it adds to the ketone to make this O minus. Instead of quenching it, it's going to do an intramolecular SN2 reaction to make an epoxide. The juvenile hormone, this is just, you can read about it. It's kind of interesting. Like I said, I don't really teach this, but it does make carboxylic acid. I do talk about this. You need to look at this where this nucleophile will do an epoxide opening. And you see that you get the anti, because it's an SN2. Here we go. An example. And you get the opening of the epoxide. And this is showing you, because these are strong, see the negative, strong nucleophiles, they're going to open in an SN2 fashion from the least substituted carbon. How do you make this tertiary alcohol? Okay, well, notice that these are the same. So you can make this from this Grignard, this ethyl Grignard, and then you would want to quench it with water, acid, a little bit of acid in the water, and that would come from a leaving group if it's going to add twice, so an acid chloride. If you wanted to do, it's a tertiary alcohol, so these acid chlorides or an ester will react with Grignards to make tertiary alcohols. If you wanted a ketone, it would have to be where this is an ethyl ketone, and then you could react it with the Grignard, ethyl Grignard, and then a little bit of acid water, and that would give you a tertiary alcohol. what is the major product here? Well, this is your nucleophile. It's an acid-base reaction where the pK of that hydrogen is 25. So the first step, you generate this alkyne-ide. So it's a negative carbon. Nucleophile, you have an ester. And so esters are going to add, these will add twice. So this is a leaving group. The first addition is going to make this. So we got 1, 2, 3 carbons. And then you see this is a ketone, which is going to be more reactive. So you're going to have another addition of the alkanide. So you're going to get 2 additions, and it's going to be a tertiary alcohol. C. So when you're thinking retrosynthesis, you need to recognize that the tertiary alcohol can be synthesized using a Grignard reagent, and you can add an R group. And so here comes from a ketone. And so here, when you have this compound, if this is the product that you are making, if you break one of these, one ethyl, then it came from the aldehyde, and it also uses the Grignard. So, and then, so you show this going forward. This is your positive, this is your negative. You get an addition there, and you get the alcohol, secondary alcohol. If you have an ester or an acid chloride, then you're going to make the tertiary alcohol. Keep in mind that these are very reactive, whereas the cuprate would actually stop at the ketone. And so here we have the acid chloride or ester, and we're going to make a tertiary alcohol. Acid chloride is going to go to tertiary alcohol. The Grignard with the ester, tertiary alcohol. Notice it's adding twice. It's adding twice. Here, it's a ketone, so it's going to add one time to make a tertiary alcohol, but this isn't going to happen. And why is that? Because you have an acidic proton. So what's going to happen is this will happen first. This will happen fastest. An acid-base reaction. So this pKa of an alcohol, of your acid, is 16. And when the CH3 deprotonates that proton, it makes an alkane, which is a conjugate acid, and a pKa of 50. So you get, this is the actual reaction. You just get an acid-base reaction. You do not get a no nucleophilic acyl addition. You do not get this. You get an acid-base reaction. So one way to do that is to, it's called protecting group chemistry. There is a big green book. Gosh, I want to say, I think it's Theodore Green. And it's all about protecting groups. And you can find different functional groups that you can kind of protect, hinder, and then so you mask them. You mask a functional group, and then you unmask the functional group. It's like you dress up as a ghost. So you are you. This is you. Okay. And then you put a ghost outfit on you. Okay, a ghost outfit. And then, so you mask yourself, but then you take it off. And then you become you again. Okay. So this is the functional group mentality. You have to do a reaction to convert the functional group to a different functional group. So functional group number 1, functional group number 2, and then you go back to functional group number 1. So you do this full cycle. So one way to protect alcohols, and a great alcohol protecting group, are these silyl ethers. And so when you have a silyl ether, now you can do whatever reaction you want, and then you can take the solid ether off. And the way you do that is as a tea bath, which I'll show you what that is, tetrabutyl ammonium fluoride. So how do you protect this alcohol? You're going to add some kind of silyl chloride. So you add some kind of silyl chloride. A lot of times you add a pyridine base in there. You'll protect that as a silyl ether. And then when you deprotect it, you use tea bath. And that way you can go ahead and then you can do your Grignard reaction. And this is shut down as a protecting group. And then you can reveal it back to its original alcohol. So this is showing you this TBDMS, S stands for silyl chloride. This is tert-butyl. So there's your tert-butyl dimethyl. So tert-butyl dimethyl, silyl chloride. And usually, okay, so I said pyridine and imidazole works. You just need some kind of base, proton, and this will do an SN2 reaction to protect that as a silyl ether. Sometimes you'll see it as just OTBDMS. And then TBAF is tetrabutyl ammonium fluoride. So tetrabutyl, 1, 2, 3, 4. Tetrabutyl, so there's 4 of them. Makes that a positive. And then the fluoride minus. And fluoride loves silica. So this will only attack the silica, and this actually is a leaving group, and it'll pick up the proton. And you see that you get the new fluoride silica bond, and this is how you deprotect. So here, if you have this alcohol here that you want to shut down, you can add TBDMS, chloride, and imidazole. You protect it as the silyl ether. And then you have this Grignard that can now do the nucleophilic acyl addition on the ketone. And then once you quench that and you get your tertiary alcohol, you want your primary alcohol to come back. So you react it with T-bath. T-bath doesn't do anything else. It just has a love for the silica. So it will take off the silica bond. And now you have a primary alcohol and a tertiary alcohol. Okay, so which reaction scheme would best work here? So you need to look at your starting material, and you see that you have a ketone and you have a primary alcohol. And what do you want to make? Well, you want the primary alcohol to stay. So you want the primary alcohol to stay. And then you see that you have a ketone here, and now you have a tertiary alcohol. You see that this is the carbon there, and you have your ring. So all these stayed. So the only thing that's new is this group here, and this phenyl group has introduced here. So you need a phenyl Grignard to add to the ketone. And then you'll also need H3O plus, because this will be a 1 and then a 2. However, this is going to do an acid-base reaction with this acidic proton here. So we need to protect this with a silyl ether. So there we go. This is number 1, the silyl ether. And then what you would do, number 1, you sometimes would want to draw that out before you go to the next. Tert-butyl dimethyl silyl ether. And now you have your ketone. So that's step number 1. And then this is step number 2. And so this nucleophile will come here. And then with the water, you get protonation to make this compound. Where the phenyl has been added. And then you want to unmask the silyl ether back to the alcohol product, and this would be T-bath. And so where's T-bath on here? So that's number 1. Do we see the Grignard? Phenyl Grignard's number 2. This would be number 3, and then number 4 would be T-bath. Do we see T-bath? There's number 4. So do we see number 1? Number 1 is here, number 1. Number 2, number 3, and then number 4. So B is your answer. This is just showing you more mechanisms where the Grignard will nucleophilic attack an acid chloride or an ester, and you'll get 2 additions to make the tertiary alcohol. This is just showing you the organocuprate. However, with acid chlorides, we'll stop at 1 addition, so we'll get the ketone. I think esters do actually react, so I'm going to disagree with that on the previous slide. An alpha-beta unsaturated ketone, you sometimes get this resonance. Oh, okay, so this is, we talked about 1,2 addition versus 1,4 addition. So this is for when you have a unsaturated substrate, and so because you get resonance, some nucleophiles will add 1,2 and some nucleophiles will do 1,4, and it really depends on the metal. So Grignards, so a Grignard is a magnesium nucleophile or a lithium, and they always do 1,2 addition. So the nucleophile is going to add to the 2. So this is a 1, 2, 3, 4 complex, and so you're going to get 1,2 addition with the Grignards and the organolithium. However, cuprates are going to do, they're considered soft metals. So like if you got an ethyl cuprate, you'll see this is 2. That's going to do a 1,4 addition. And so this is going to be a positive, negative. So this negative carbon, which I added an extra carbon, didn't mean to. So this negative carbon is going to add to the 4, and then this goes here and this goes there. So you get this the cuprate, so the ethyl 1, 2 goes there. This is the 4 carbon, 3 carbon. Now the double bond has gone here, and this is the 1 atom, and then it's going to pick up the water. So you see the H is added to the 1 position, and then the 4 position has this. Now you might not see that because you're like, oh, it's added to the 3 position, but let me show you something. What happens is you get this molecule, right? Okay, so this is where you added the ethyl, and you can call that 1, 2, 3, 4, where you added the ethyl, the cuprate to the 4, but this is an enol. An enol tautomerizes, and so 1, 2, 3, and so there, then the hydrogen will add there, and the double bond goes away, and you make your ketone. And so this is showing you 1,2 addition. You get this with the organolithiums. You get this with the Grignard. And so here it adds the 1, 2, and that's what we've been seeing. And you keep the same double bond. Here, if you do a 1,4 addition, the nucleophile, and this would be for a cuprate. So if you did something like the cuprate here, and that's the methyl, it's going to add here. So this would be a new methyl. And this proton, you can do it this way where the proton picks up here, or you can see that that's an enol, and the enols tautomerize to the ketone. So 1, 2 versus 1, 4 is showing you that the organometallics, organolithium, undergo 1, 2 addition. You always get 1, 2. The cuprates undergo 1, 4, so they're going to add here, and then you're going to see The R is going to add and the hydrogen adds, so the double bond disappears here. So whenever you see this 1, 2, 3, 4, this is the 1,4 addition. And so that's showing you. You can also do carbon dioxides. I'm not too worried about that. And epoxide openings. This is just showing you the leaving group, if whether you have an addition versus substitution. I think this is just a summary. Okay, how about looking at synthesis reaction? So ultimately, if we want to start with some kind of secondary alcohol and we want to add a nucleophile, these you need to think of all of the reactions. You can make an alkene using elimination with sulfuric acid. You could oxidize it now, an alcohol, to a ketone, oxidation, and now we can add nucleophiles by a 1,2 addition to the ketone here. We can convert the OH into an alkyl halide and make it a great leaving group and make an alkyl halide, or we can make it a tosylate. So these are ways you can convert alcohols to lots of different functional groups. So how would we synthesize this? Well, we want to come up with an alcohol that contains only 4 carbons. So we could do 1, 2, 3, 4. So you can make that as a 4-carbon alcohol. That would be one way. 1, 2, 3, 4. You can't go the other way because that would be 5. So if you have an alcohol containing, so what is this? This is a primary alcohol. And what do we want to add? We want to add this compound here. So this could be a nucleophile, right? How do you do that? Magnesium bromide, right? A Grignard. And then of course the acid and water quench. But this is not going to react with the alcohol, so you need a ketone or an aldehyde. You need aldehyde. So how do we convert that to an aldehyde? I got too many carbons. 1, 2, 3, 4. 1, 2. Yeah, let's make sure we only have 4 carbons. 1, 2, 3, 4. So if we have this aldehyde, how do we do that? We do the oxidation with PCC. So PCC oxidation to the aldehyde, step 1. Step 2, the Grignard, and then quench. And that, what does that make? Does that make an alcohol? So, and then we're adding this carbon here. That makes it a secondary alcohol. So then we're going to have to oxidize that. You can oxidize it with PCC again. And so here you're seeing, or you could do an SN2 reaction. Oh, they're showing you how to make the Grignard. I'm okay with you just, if you want to make that the Grignard. PCC is oxidizing it to the aldehyde, but then you're going to have to do another oxidation to make it back to a ketone. Okay, so how would you do this? This would be something to look at here. This starting material, you're going to see that it stays, right? So what's been added here? The only thing that's been added here is this aldehyde, and it's been added para. So the first thing you want to do is you want to shut down that OH. So you're going to need to do a protecting group. 1, 2, 3. 1, 2, 1, 2, 3. You need a protecting group. Protecting group could be the tert-butyl dimethyl ether and imidazole, or you could use pyridine. Remember TBDMS chloride. So that's one way to convert that to the protecting group. And then you can do Friedelscraft acylation of an aldehyde. Um, so you can just do aluminum trichloride. Okay, here we will talk about nucleophiles added to weak compounds with catalytic acid. This will be the next chapter. So you will have to know this mechanism, and you can read about it, and I'll talk about the next chapter. But you'll protonate the alcohol, the protonate the carbonyl oxygen, and then the nucleophile will add, and you're going to have a hemiacetal. That's a new functional group. And then you're going to have to protonate the OH to water to make it a good leaving group. And then you will reform the carbonyl, and water will leave, and then your nucleophile will add again. And so there's going to be 6 steps in this mechanism, and your new functional group is going to be an acetal. And this is an important functional group as our biological sugars all form hemiacetals and acetals, and so do our nucleic acids. So that wraps up this chapter.